Hello and welcome to a video AI for truss analysis. The truss that we have been given is stated here with the applied loads of 50 kips at joints C and D, and the dimensions are as shown. In this problem, we're going to first find the internal forces in members AH and CD. We will then design member CD as a square structural steel cross-section. Finally, we'll design member AH as a structural steel square cross-section. This is the first of 3 videos. In this particular video, we will be doing part A. Remembering our truss roadmap for finding the internal forces in truss members, the first thing we must do is identify our members of interest. In this case, AH and CD. The next thing to identify are our zero force members. We have 2 rules for zero force members, the 2-member rule or the 3-member rule. In this case, we do not have any members that meet the 2-member rule, that being 2 non-collinear members joined at a joint with no external load. In this case, we do have 2 members, however, that are zero force members because of the 3-member rule, where 3 members are joined at a joint, in this case joint B. 2 of those members are collinear. 1 member is non-collinear. There is no load or reaction at the joint, so the non-collinear member is a zero force member, the same thing being true when we examine joint G. With that information, we can now begin to move forward in our process, and we need the external reactions. In order to find the external reactions, we need a free body diagram of one big body. Including all of our external forces acting on this body. We have a 50 kip load and a 50 kip load, and our reactions, in this case a Y reaction at the roller at E and an X and a Y reaction at the pin at A. In order to make a complete free body diagram, we need our coordinate axis system, X and Y, and we need to make sure that we denote all of our dimensions. We're now ready to make use of our equations of equilibrium, but before we can make use of our equations of equilibrium, we must classify this force system. This force system is a non-concurrent force system, as the lines of action of all of the forces do not intersect at a single point. Since it is non-concurrent, we have 3 equations of equilibrium available to us, and in this case we have 3 unknowns, that being AX, AY, and EY. So we're certainly happy that we can solve this problem. Let's first sum forces in the X direction. The only force in the X direction on our free body diagram is AX. Therefore, AX must be equal to 0. Now we could then sum forces in the Y, but in that case we would have 2 unknowns, EY and AY, so it would be wise to sum moments about a point. And in this case, let's sum moments about point A, set that equal to 0. We'll assume counterclockwise is positive. Summing moments about A will just work from the left to right. First force that we come across is the 50 kip force at a distance of 20 feet. It would tend to rotate clockwise, so that is a negative value. Next we come across this 50 kip load at a distance of 30 feet, also tending to rotate it clockwise, being negative. Finally we come across EY at a distance of 40 feet, tending to rotate counterclockwise, or a positive value. Solving this equation, we find that EY is equal to 73.75 kips. Now it's time to sum forces in the Y direction. We'll assume that up is positive. Again, working left to right, we have AY, positive, negative, 50 kips, another 50 kip load in the negative direction, and EY in the positive direction, which we just solved for as 73.75 kips. This tells us that A sub Y is equal to 26.25 kips. Now that we have our reactions at A and E, it's time to make our cuts and solve for our internal forces. Let's first look at AH. Our truss cutting rules tell us to cut through our member of interest and then cut through the entire truss. We want to then circle everything around that particular location, including all forces and reactions. That will be one cut, and that will be, we will apply, I should say, the method of joints for that portion. Now for CD, we've cut through that member, cut through the entire truss, and again draw a box around or a circle around everything. In this case, we will have to apply the method of sections to solve for those, the internal forces in those members. So let's begin by looking at finding the force in member AH, applying the method of joints. Of course, first we must draw a free body diagram of that particular joint. Let's include our 26.25 kip load or reaction, and we'll assume that all internal forces are in tension, and we'll let the mathematics tell us otherwise. Make sure that we have our x and y coordinate system. Since it's a method of joints, the only dimension that is of any consequence is this angle. Since it is 10 feet by 10 feet, we could say that's also 1 by 1, which makes the hypotenuse square root of 2. This is a concurrent force system, since all of the forces involved in this free body diagram do intersect at a single point. Concurrent force system, we have two equations of equilibrium, two unknowns in this case, so we're good. We don't care about the force in member AB in this particular problem. We're only interested in the force in member AH. So if we can find one equation that would solve for that one unknown, it would be wise to use it. If we sum forces in the y, set that equal to 0, we'll find that we can solve for the force in member AH with a single equation, 26.25 kips in the positive direction. Also, according to our free body diagram, in the positive direction is member FAH, and we want to find the vertical component as compared to the hypotenuse component. Solving this, we find that FAH is equal to negative 37.12 kips. Negative tells us that our assumed direction was incorrect, so in fact this member is in compression. Now we must attack finding the force in member CD. Again, drawing a free body diagram of our cut. And including all of our forces. We have a 50 kip load, 70.75 kip reaction, and then we have internal forces in each of these three members, and we will denote these FCD, FCF, and FGF. Let's denote our dimensions. In this case, dimensions will be critical. If we were to also note that we have joint C out here, joint G, this is joint F, D, and E. We could then also say that this is 10 feet. And finally, the angle here is 1 square root of 2 as well. Now again, the only member of interest that we're curious about finding is the force in member CD. So if we can find one equation with one unknown, that unknown being the force in member CD, save ourselves time. In this case, we will go to our most powerful equation of equilibrium, that being the sum of the moments. If we can find a point where two of our unknowns intersect, in this case joint F, summing moments about that point, neither of these two, that being FCF and FGF, the force in those two members, their lines of action pass through that point, meaning they have no moment about that point. So if we're now summing moments about point F, we have the force in member CD times a distance of 10 feet, tending to rotate it clockwise, so that's a negative value. The 50 kip force also passes, its line of action passes through joint F, so it does not have a moment, and we have our 73.75 kip reaction, force times a 10 feet perpendicular distance to that point, tending to rotate it counterclockwise, a positive value. Therefore, the force in member CD is 73.75 kips comes out positive, meaning our assumed direction was correct. It is in tension. There are our answers.